This video will discuss the Big Ideas document that reviews Chapter 18 and 19 from the Holt science textbook. Chapter 18 and 19 goes into much more detail about astronomy. We only read a few select, about 10 pages from those two chapters. And you might have taken some detailed notes or looked at all the vocab words and thought that it was still a lot of information. But this sheet here with the 10 points are kind of boiling down those two chapters into what we're really focusing on. And remember that we are focusing on astronomy as a way, like kind of a physical example of physics at work. So when we're talking about speed, velocity, and motion and forces, one way that we'll look at that is through mousetrap cars and solar cars and examples in class and the labs that we do in class. But astronomy is another way where we see all of those things happening and playing out in real time out in space. So the first one asks, what does the discovery of the Doppler effect tell us about the universe? So the first thing we should figure out is, what is the Doppler effect? The Doppler effect is that radiation, electromagnetic radiation, looks different depending on the direction that it's going. So in particular, there's something called redshift. Sorry, my handwriting there is horrible. Let's try that again. Redshift. Redshift tells us that lights, meaning stars, that are moving away from us appear red. So Hubble looked out through his telescope and found that almost all of the stars in the night sky have a slightly reddish tint to them, essentially. A slightly red shift of the electromagnetic radiation. And so what he discovered is that when lights are moving very, very, very quickly in a certain direction, towards or away from us, they will appear a slightly different color. So when lights are moving really quickly towards you, they appear blue. When they're moving really quickly away from you, they appear slightly red. This is the same effect of how a fire truck will sound slightly different in terms of pitch of the sound when it's moving towards you or when it's gone past you and is moving away from you. That pitch changes just a little bit. So that's the same thing for these stars. So he found that pretty much all of the stars out in the night sky appear slightly red. So if they appear slightly red, it means they're moving away from us. So if all of the stars and solar systems are essentially moving outwards and expanding out and moving away, that means one thing. It means the universe is expanding. So more importantly, or maybe not more importantly, but just as importantly, if everything is expanding outwards, if everything is moving in one direction, it had to start somewhere else. So if we rewind this expansion, that means that everything had to start grouped and clumped together at some central point. So this was the first time that people started thinking about, wow, where did all of this come from, and have a theory to describe that called the Big Bang. Right? So if we rewind that expansion, we get to the Big Bang. So in number 2, it's asking about why different types of telescopes are placed in different places. One thing that's important to understand is electromagnetic radiation is not just a scary word for radiation, right? But light is a type of radiation. Another type of electromagnetic radiation is X-rays, gamma rays, UV rays, etc. Radio waves. So a lot of those types of radiation, like X-rays and gamma rays, don't reach the Earth's surfaces, which is good. The atmosphere blocks X-rays and gamma rays. So since that happens, if we want to look at space through one of those telescopes, right, through a telescope that looks at X-rays, we can't have that telescope on Earth. That telescope needs to be up in space. So this question is really just getting you to think about, well, the reason that we have a lot of telescopes in space is not to get closer, right, because the galaxies and the solar systems that we're looking at are still thousands and thousands of light years away, but it's to get outside of our atmosphere because our atmosphere blocks gamma rays and X-rays. We're going to boil solar system formation down just to kind of 2 main steps. You start first with a nebula, and that nebula is the cloud of dust and gases And normally that nebula is kept just kind of in balance, floating around as a supermassive cloud because of the force of gravity pulling objects together, which causes them to bounce off, the dust and the rocks and whatever, to bounce off of each other, and then the pressure of them moving outwards, right? So that pressure and that force of gravity are balanced. The cloud continues being a cloud until that nebula collapses. Now, the reason why, I didn't spell that right, the reason why it would collapse is because a nearby star explodes and sends a shock wave of energy and therefore force into that nebula, causing everything to clump together. Or one nebula could collide with another nebula. As those two nebulas collide together, there's a huge amount of mass that increases the force of gravity. Therefore, everything starts to collide down and compact in the center. So as things compact in the center, there's so much mass in the middle of that collapsing nebula that mass is slamming into itself, and it starts fusion. It's so much friction, so much heat, fusion starts up, and that is the beginning of a star. Around the perimeter of that collapsing nebula, where it's a little bit cooler, those pieces of dust start to collect into tiny pebbles, into smaller rocks, those rocks into boulders, those boulders into planetesimals, and planetesimals all collide into planets. Newton's law of gravitation essentially says that planetary objects are going to have more or less gravity depending on the mass of the two objects and the distance between those two objects. And remember, we're talking about planetary objects. So we're talking about planets, and we're talking about moons, and we're talking about stars. We're not talking about humans or objects on Earth. We have a tiny bit of gravity, but we essentially have no mass compared to the Earth. So therefore, when we're trying to quantify how much gravity a human being has, it's essentially zero, which is why we're only going to talk about planetary objects in this way. So what he discovered is that that mass and distance are essentially inversely related to the amount of gravity. So if you take the mass of object 1 times the mass of object 2 and divide it by the distance squared, that describes the gravitational pull between two planets. So the mass of planet 1 times the mass of planet 2. So the bigger that those two masses get, the greater the gravitational pull. Reverse, the larger the distance between those two objects get, the smaller the gravitational pull. So this is just kind of setting up a law that's going to help us to understand Kepler's three laws down below. But essentially, the larger, the heavier the planets are, the more gravitational pull they're going to have. So the sun has a greater gravitational pull than the Earth because the sun has a larger mass. Now, the farther apart the two objects get from each other, the less gravitational pull that they're going to have on each other, which makes sense. If they're super far apart, they could have essentially no gravitational effect on each other because that distance is so big. When talking about Kepler's laws, we're not going to get bogged down in all the details, so this is going to move kind of quickly through this. But Kepler's first law is that planets move in an ellipse. So a circle that's kind of flattened, right? So rather than that, they move slightly like that, okay? Kepler's second law is that by doing some math, he figured out that planets that are closer to a star than planets that are further away from a star move faster. And the farther out in the solar system you get, the slower those revolutions happen. Now the book just kind of makes that claim, right? It just says, well, if a planet is closer and a planet is farther, it has to, it's going to move faster if it's closer and it's going to move slower if it's further, and doesn't really explain why that's the case and why one planet is moving faster and one planet is moving slower. Which is why, in the big ideas, we start with Newton's law of gravitation. Newton's law of gravitation says there's a larger gravitational pull. Remember, gravity is force if those two objects are closer together. and there's less gravitational pull, so therefore less force, if those two objects are further away from each other. So if we're thinking about Newton's law and applying it to Kepler's second law, where if a planet is closer to its sun, that means there's going to be a stronger gravitational pull. If there's a stronger gravitational pull and a stronger force, that means that that object is therefore going to be moving faster, right? Because force results in acceleration. Conversely, the farther out a planet gets from its star, it means that it's going to be moving slower because there's less gravitational pull, there's less force causing that planet to move in the first place. So for Kepler's third law, what I've written is that he figured out that you can calculate, you can predict a planet's distance from its star based on how long it takes for that planet to revolve around its star. So essentially we're applying Kepler's second law and drawing some inferences from that. If we know that planets that are closer to a star move faster and planets that are further away from a star move slower, we can therefore watch a planet revolve around a star, and we can say, okay, this one revolves in 800 days, this other one revolves in 200 days. We can actually calculate that the one that revolves in 200 days is a lot closer to the star than the one that revolves in 800 days. And actually, we can predict almost exactly how far away that 200-day revolution planet is compared to the 800-day one, with using Kepler's math. We don't need to worry about the math. We don't need to do any of those calculations. We just need to understand what he's able to draw and able to calculate and able to predict from this. So if we know how fast a planet goes around its sun, how fast it revolves, then we can predict how far away it is from that star. So now you might be thinking, okay, great, we've figured out that planets move in an ellipse, that they revolve faster if they're closer and slower if they're further, and therefore we can predict distance from a star based on revolution around a star. Who cares? So, amazingly, that's question number 8. Why do we care about Kepler's laws? Well, distance away from stars is very important. If I get too close to a star, what happens to me? I burn up. If I'm too far away from a star, I freeze to death. Now, in my daily life, that doesn't really matter because I'm not traveling closer or further away from the sun. But if we are looking out into the universe and we're looking at different solar systems and we're looking at different planets revolving around different stars, we want to know which of those planets are too close or are too far, and which of those planets are just right. Just right for what? Just right for life. Right? If they're too far away from a star, it's going to be too cold. Liquid water would freeze. If it's too close, liquid water would actually burn off, and there wouldn't be any liquid water. Right? So what we're looking for is we're out there looking for planets that revolve around their sun in give or take 300 to 500 days, depending on the brightness and how hot a star is, but in a medium speed around a sun, so that we can tell that they're a medium distance away from a sun, which indicates that there's the potential for life. So all of these things help influence our search for life on other planets. So with 9 and 10, I'm going to actually answer number 10 first. Why are the planets moving at all? Well, the planets and the stars, and this goes back to question 1 about what Hubble saw with redshift, everything's moving and rotating and revolving, and the universe is expanding outwards, all because of the Big Bang. So this question of why the moon doesn't crash into the Earth is the same as why doesn't the Earth crash into the sun, right? And really, it all has to do with vectors. So if we have here Mr. Sun, right? Don't know why it's not Mrs. Sun, but Mr. Sun here, and we have a planet that is moving in this path. The sun's gravity is going to pull it in that path. Now, as we learned, when we're looking at force and when we're looking at velocity, if there are two different forces acting on an object at 90-degree angles, the planet, or the object, moves at 45 degrees. It'll actually travel that way. So now the planet would continue on in that way, except that gravity is going to pull it towards the sun there. So the planet would then move this way, and the planet ends up over here. It would continue moving over there, except that gravity would pull it in that direction. So the planet would actually go over here. If the planet is over there now, it would continue moving that way, except the sun's going to pull it over there, and its resultant pattern, its resultant motion will go in this direction. And as you see, if we continue this pattern, what ends up happening is the planet continues to move in it didn't work out perfectly, but right, it moves in a circular pattern, and what we end up with is more or less our ellipse of a pattern around, or an elliptical revolution around the sun. So, in answer to number 9, why doesn't the moon crash into the Earth? It's because the force of gravity and the force of the Big Bang are opposing forces, which is crazy to think about. That nearly 15 billion years after the Big Bang, the force of that initial Big Bang is what is still causing planets to rotate, revolve, and all solar systems and galaxies to expand outwards in the universe. So all of that force is still acting on all of the objects and all of the matter in our universe, causing rotation, revolution, and expansion of the universe. And because force of gravity and force of Big Bang are opposing each other and act at about 90-degree angles, they therefore result in approximately 45-degree angle pattern of motion, which results in a near circular revolution. That near circular revolution is called an ellipse, which gets us back to Kepler's laws. So as you've seen here, all of these laws are tied directly to physics, and some of them tell us some really important things about the expansion of the universe, about the Big Bang, and about looking out into the universe and being able to predict what planets may be possible for life to inhabit, and where we could either potentially go and move the human population to, or where we could go and find extraterrestrial life living out there. Lots of possibilities.